Okay, folks, so back by demand, I'm working through test 4, showing all the work as best as I can. Due to the nature of this test, I've worked it through chapter 9, 10, and 11 in the Adam's First book. So, question 1. Given the following reaction between sodium metabisulfite and dissolved gold chloride, what mass of solid gold could be precipitated from 150 grams of sodium metabisulfite? So I'm given one mass, and I'm asked to find this, grams of this. So that's a simple grams to moles to grams type situation. We go 150 grams of sodium metabisulfite, Na2S2O5. We need to find the molar mass. To find the molar mass of this. So sodium is 23. Sodium is 23 times 2, plus sulfur is 32 times 2, and oxygen is 16 times 5. That is about 190 grams per 1 mole. And we use our balanced chemical equation. We need a balanced chemical equation. For every 3 moles of sodium metabisulfite, we'll get 2 moles of gold. And finally, in 1 mole of gold weighs about, we'll say 197 grams. It's close enough. Might be a little off. But running that through, 150 divided by 190 times 2 over 3 times 197 gives us, how many grams should we get? 103.7 grams. Answer D. In the decomposition of 38 grams of potassium chlorate, 20 grams of potassium chloride forms. What is the percent yield? So I'm given 2 masses, a mass of reactant and a mass of product. That's a dead giveaway. It's a percent yield problem, even if I didn't already spell that out. So this is our actual, and we need to calculate our theoretical. So to calculate our theoretical, we start with 38 grams of KClO3, and we need to convert this into grams of KCl. So grams per 1 mole. K is about 39.1. Cl is about 35.45. O is 16 times 3. That's about 122.55. For every 2 moles of KClO3, we produce 2 moles of KCl. It's a 1-to-1 ratio. And KCl is just 74.55 grams per 1 mole. So let's figure out, what is my theoretical yield? 38 divided by 122.55 times 74.55 is 23.12 grams. That's a theoretical. So 20 divided by 23.12 times 100, that's about 86%. So answer C. And question 3. When oxygen is scarce and human muscles can convert glucose to lactic acid for a quick burst of energy following the bond reaction, 1 glucose molecule breaks apart into 2 lactic acids. If 328 grams of glucose were to be fermented in this way, how many grams of lactic acid could be formed? This is a bit of a trick question. So for every 1 glucose, you form 2 lactic acids with no waste. There's no errant molecules formed. So if 328 grams of glucose were converted, they would convert into 328 grams of lactic acid. We are not losing any mass to like lost oxygen or anything like that. So it's just straight 1-to-1. Now, moles wise, if I converted this into moles, 1 mole of this is converted into 2 moles of that. But the fact that 1 mole of this weighs half as much as that, it's going to work its way back out. Now, scroll down real quick. Anhydrous magnesium sulfate can absorb moisture to become a hydrate epsomite, Epsom salts. If magnesium sulfate plus 7 waters forms Epsom salts. If 15 grams of water and 15 grams of magnesium sulfate are mixed, what mass of Epsom salts could be formed? So I've been given 2 masses, both reactants. That is a hint that this is a limiting reagent problem. So I'm going to go 15 grams of water, 2 Epsom salts, and 15 grams of magnesium sulfate to Epsom salts. MgSO4. So the molar mass of water, 18 grams per 1 mole. Molar mass of Epsom salts. Magnesium is 24 plus 32 plus 16 times 4. It's 120 grams. Now you may think, well, 120 grams is a lot heavier than 18 grams, but however, for every 1 mole of Epsom salts, we need 7 moles of water. And for every 1 mole of Epsom salts, we need 1 mole of magnesium sulfate. And the molar mass of Epsom salts would be just magnesium sulfate plus the 7 waters. So 120 plus 18 times 7 is going to be, and 1 mole of Epsom is 246. So let's do this. We choose the lower of the 2 numbers. 15 divided by 18 divided by 7 times 246 gives us 29.3. And the other one, 15 divided by 120 divided by 1 times 246 is 30.7, 30.8. So which one do we choose? 30.8 or 29.3? We choose 29.3. We choose the lower of the 2 values. In lab, we diluted 10 mils of vinegar to 50 and then titrated 12.5 mils with a base, with 0.125 molar base. We took 22 mils of base to neutralize the dilute vinegar. What is the original concentration? So M1V1 equals M2V2. We're given 2 molarities, 2 volumes, and a molarity. That tells us we need this equation. So the molarity of our acid times 12.5 equals the molarity of our base, which is 0.125 times 22. So let's first calculate the molarity of our dilute acid. So 22 times 0.125 divided by 12.5 gives us 0.22. Now that 0.22 is then was from originally a 50 ml solution. So the M original, which was a 10 ml solution, so we're going to say 0.22 times 50 divided by 10 is going to be our original concentration. So the original concentration is 1.1 molar. 1.1 molar. However, this is probably harder than I'm going to ask on the test this year. Moving right along. Problem 6. Problem 6. How many grams of barium hydroxide are dissolved in 0.141 liters of 0.237 molar solution? So We got a molarity, we got a volume. I'm asking for grams. That's where I'm going grams, molarity to grams instead of grams to molarity. But that's the basic premise. Molarity times volume equals moles. Moles times molar mass equals mass. So first step, find our moles of barium hydroxide. 0.237 times 0.141 in liters would give us our moles. 237 times 0.141 is 0.033. Now we have to use our molar mass. 334. Barium. I'd like to say barium is 137. 137.3. And each hydroxide is 17 because it's one oxygen at 16 and one hydrogen at 1. So the total mass is 171.3 grams per 1 mole. So times 0.0334. How many grams? You would only produce a measly 5.72 grams. What is the concentration of a 27 ml solution of sodium chloride if we add 23 mils to of a 0.25 molar? So this is a little bit of a trick question. 27 mils of pure water. We only need to consider volume total, volume of solution. So we do not consider the 27 mils, but the M1, V1, that's 0.25 and 23 mils. But the V2 is not 27. It is 27 plus 23, which is, in case you don't know, 50. So 0.25 times 23 divided by 50 is about 0.115. So the correct answer should be C. Antacids such as aluminum hydroxide neutralize excess stomach acid via reaction. What volume of this stomach acid could be neutralized by 15 grams? So we're given 15 grams and a molarity, and we're asked to calculate a volume. So that's a grams to moles to volume type problem. So start with 15 grams of aluminum hydroxide, and we go, what is the molar mass of aluminum hydroxide? Well, aluminum is 27, hydroxide is 17. There are 3 hydroxides. So the molar mass is 78 grams of aluminum hydroxide per 1 mole. Now, 1 mole of aluminum hydroxide neutralizes 3 moles of HCl. So this will tell us how many moles of HCl we will neutralize. So we will successfully neutralize 0.57, we'll say 7 moles. Well, moles divided by molarity will equal our volume. So 577 divided by 0.0316 gives us 18.3 liters. 18.3 liters. A rather large amount, considering it's a rather dilute stomach acid. So we don't need to take very much aluminum hydroxide to neutralize a lot of stomach acid. Last problem on this page. This is the start of chapter, of chapter number 5. Yeah, lost a little bit of, kind of goofed a bit. But we'll need this for the next. Problem. I'll keep it nearby. How much energy could be generated by the fermentation of glucose? So to do this, what we're going to do is use Hess's law. How do you know we need Hess's law? We have two equations. So we need to match those equations to the ideal equation. So first things first, I look at glucose. Glucose appears here. It only appears there. So with that in mind, we use that equation as written. We use that as written without modification. Now for our lactic acid appears here, but it's on the wrong side, right versus left. And there's 2 moles as opposed to 1 mole. So to fix that, I have to multiply that by -2. So that's going to switch this equation to 6 waters, and 6 CO2 goes to 6 oxygen and 2 lactic acids. And of course, multiply that by -2. So when you do that, the 6 waters cancel out there, the 6 CO2 cancel out there, the 6 oxygen cancel out there. You get your overall equation. That becomes 2, 6, 8, 8. So when I add these two equations together, I'm adding 2805 plus positive 2688, and that'll be our energy. 2805 plus 2688 gives you -117 kilojoules. That's our answer. Okay. Okay. So, number 10. 25 grams of an unknown metal is heated up to 100 degrees C and dropped into 30 mils of 25-degree water. Heat capacity of this. If the water heats up to 28.4, what is the metal made of based on a specific heat capacity? So the fact that we have specific heat, we know it's a Q equals MCAT. This is similar to a homework problem, so while it's a little bit challenging, it is not too bad. And the idea of Q, negative Q of the metal equals Q of the water. So the Q of the metal is M of the metal, C of the metal, delta T of the metal. And Q of the water is M of the water, C of the water, delta T of the water. So 30 grams of water, because it's 30 mils. Specific heat of water is 4.184. And the delta T of water is heated from 25 to 28.4. So that's 3.4 degrees. The metal, we have -25 grams. We don't know the heat capacity of metal, but we know it cooled down from 100 degrees to 28.4 because the water and the metal get to the same point. So on the right, 30 times 4.184 times 3.4 is, we'll say 426.8. And on the left, or minus 100, that's 71.6 times 25. You got 1790 C. So solving for C, 426.8 divided by 1790, you get something that C that looks like 0.238, which is closest to silver, which means our metal has to be silver. Okay, what is the delta H for the formation of 1 mole of potassium chloride for the following reaction? So we got to use this data. So products minus reactants. Because I have the table, we have to do products minus reactants rather than Hess's law. So KCl, 435.9, plus we have NO2s, 90.4, positive times 3, because there are 3 of them, minus these guys, -391.4, and 33.9. And there's 3 of them. So negative 4, 35.9 plus 90.4 times 3 is negative 164.7. Negative 391.4 plus 33.9 times 3 is negative 289.7. Negative 164.7 minus a negative 289, which is the same as plus or positive. It's going to be positive 125 is my answer. Positive 125. What would the enthalpy of reaction be for the following for boric acid dissolution in boron trioxide? A lot easier problem here. Still the same equation, negative 194.33. There's 2 of them, so times 2. That's negative 2188.66. And then we have negative 1273.5 and negative 285.83 times 3 because there's 3 waters. That will give you negative 2130.99. You minus a negative 2188.66 plus 2130.99 gives you negative 5767. Okay. Once again, we had an issue printing. Oh well, we'll deal with this. The gas expands inside a container while cooling by 300 joules. What if the internal energy is negative 450? How much work was done by the system? So delta U equals Q plus W. Delta U is negative 450. When it cools, it is losing heat. So it's negative 300 joules. Now, the fact that gas expands tells us that it's negative work as well. Negative work. However, we can just check the math. The difference between W and this would be have to be negative 150 joules. Negative 150 joules. Okay. In order to forge weld 2 iron bars together, metal needs to be heated to 1260 degrees C. If the specific heat capacity of iron is 4.49, how much heat is required to heat 141 grams to 25 degrees up to the forge weld temperature? So heat, we have heat capacity. So these hints tell us this is a Q equals M cat equation. So we are trying to solve for heat, solve for Q. So we have 141 grams. We have heat capacity, which is 0.449. And we have our change in temperature, which is from 25 degrees to 1260. So that's 1235 degrees. You do this, 141 times 0.449 times 1235, you get something like 78,186 joules. So to turn this into kilojoules, divide by 1,000, you'd get the answer C. Problem 15. Define a state function. It's a path-independent function or a function that only relies on starting and ending point. Examples are delta H, delta U, delta G, delta S. It's a path-independent function. Now, what does that mean? It means you can solve it multiple different ways and you should still get the same answer. Spooky. Okay. Moving on. Last chapter's worth of problems. So the gas chapter. Tungsten hexafluoride, one of the heaviest gases often used formation circuit boards and semiconductors. The density be of tungsten hexafluoride at 25 degrees in 1 bar. The fact that it's density tells us we need the density equation. That density equals P times molar mass over RT. Now, R will always be given. However, what happens if you accidentally use the wrong R? Not much. You usually get the same answer. So don't worry about that. T is 25 degrees. We add 273, so it's 298. The only thing we have to do is find out what's the molar mass of tungsten hexafluoride, WF6. Tungsten, I think, is something like 183 point something, at 183.8, and fluorine is 19 times 6. You get something like the molar mass being 297.8. So plugging these guys in, you get 1 times 297.8 divided by R divided by 298. You do this math, you get 12 grams. 12 grams. Everyone knows that breathing helium raises the pitch of your voice, but few know that argon will lower the pitch. Comparing the two balloons, one argon, one helium, stored at 25, how much faster will helium go flat compared to argon? When you hear words like faster or speed, you need to think about the Graham's law. So R of helium over R of argon will give us the rate comparison. So rate of argon's about 40. Helium's about 4. This simplifies to the square root of 10, which is about 3.16. You should always get a number that's greater than 1. This is the number you get if you forget the square root. But that's that. Okay. 50 grams of an unknown gas has a volume of 17.71 liters, 1 bar. Temperature 0 C. What is the molar mass? The fact this is molar mass tells us this is our density problem. But we don't have a density, but we can find a density. Density is mass over volume. So our density is 50 grams divided by 17.71 liters. You do that, you find a density is something like 2.82 grams per liter. So density equals P molar mass over RT. We're solving for molar mass. You have density times RT over P equals molar mass. So plugging those in, 2.82 times R times temperature, 0 degrees goes to 273 Kelvin, divided by 1. Your answer has to be, you solve that, you get 64. Now, Space Station Skylab used a molar ratio of 70% oxygen to 30% nitrogen at a total pressure of 5 psi. What is the partial pressure of oxygen? So partial pressures and the fact there's mixtures of gas all tell us this needs to be a Dalton's law problem. Dalton's law problem because it tells us mixtures and partial pressures. No other gas problem talked about more than one gas except for maybe the fusion one. So all the other ideal gas problems are not talking about mixtures. So to do this, it's P total times the mole fraction would give us our partial pressure. So 5 times mole fraction of 0.7 would give us our partial pressure of set 3.5 psi. Almost done. Decompression sickness is caused by the rapid expansion of high-pressure dissolved gases within the body. If a diver rapidly ascends from a depth of 200 feet, the pressure has changed from 105 psi to 14.5 psi. If nitrogen in the bloodstream was 5 mils, what would be the new volume? So I know this one is a P1 V1 equals P2 V2. The big hint is the fact I have two pressures. So that tells me I need this equation rather than the standard ideal gas. Now, I do not have to convert anything because if this is in PSI and that's in PSA, they cancel out. So 101.5 times 5 divided by 14.5 would give us our pressure, our volume of 35. Okay. In van der Waals gas, the pressure in term changes to P plus N squared A over V squared, and the volume term changes to V minus NB. Constant B accounts for what aspect? B is our atomic size. N is our amount. There's no charges, and repulsive forces are our A. Our attractive and repulsive forces are our A. So, just breaking down. Avogadro's law states that volume is directly proportional to what? Avogadro is known for Avogadro's number, which is atoms to moles. So he related to moles. Refrigerators work via forced compression and expansion of gases to transfer heat from inside the fridge out the back through a heat exchange pipe. Gas is allowed to expand from high pressure region 800 torr and 60 degrees C, 333 Kelvin, to a low pressure system of 600 torr. How many degrees Kelvin will the temperature drop? So this one's a P1 over T1 equals P2 over T2. So rearranging this, you can get T2 equals P2 T1 over P1. So you have 600 times 333 divided by 800. That would give you something close to 250 Kelvin. However, that is not the answer. You want to see how much will it drop in this problem. This is a tricky problem. This is really hard problem. You take the difference, you get something like 83.3. Because it's not 250, it's like 249.7, but yeah. Or 250, I don't know. Yeah, 249.7. Recent news, scientists found a molecule on Venus that may be indicative of life. Earth, 1 mole of gas takes up 22.4 liters. How much would the same mole of gas take up on Venus with an ambient pressure 464 and 92 bar? So this one is just a PV equals nRT. We want volume. We're given moles, temperature, and pressure. Moles, temperature, and pressure. So we're given 3 of the 4 variables, and we're asked to find the fourth. So V equals nRT over P. N is 1. R is R. T is 373. And P is 92 bar. You do that math, you get the answer is 0.666 liters. Last problem. Gas in the lower troposphere It's a molar density of 22.4. 1 mole of gas would travel to the upper troposphere in the tropic balls. It would expand to a volume of 90.6. External pressure of 200 millibars. What would the temperature be? So same problem, except instead we're now doing PV over NR equals T. PV equals NR T. So pressure, 0.200 bars. 1 millibar, there's 1,000 millibars in 1 bar. So that's a little tricky thing. Now it's 90.6 liters divided by 1 divided by R. You do that, you get something like 217 Kelvin. 217 minus 273, it's like 55. Your answer is negative 55 degrees. It has dropped to negative 55 degrees. Okay, so that was the test. I know I went fast. You can slow it down if you need to, but I got things I need to do. So hopefully this will be proof of some use to you as you're working, as you're trying to study for test 4. Good luck, goodbye, so long, and good luck.